today. So today I am going to discuss about the some common refractive mathematical representation. Okay. So first of all, we will come about the uh, gross and net retinoscopy. So sometimes in the exam it has been come as a MCQ question, like if a person has the prescription power of like for -4 with -1 180 degree, it is the gross retinoscopic value, where the working distance is 67 centimeter. So what will be the net retinoscopic value, right? So the net retinoscopic value means you have to reduce the working distance from the gross value, but you have to keep in mind that the working distance, so the dioptric equivalent will be 100 by 67 is equals to 1.5 diopter. So this 1.5 diopter you have to reduce only from the spherical power, not from the cylinder. So the net retinoscopic value, the final answer will be, so -4 minus plus 1.5 minus 180. So it will be minus 2.5 sphere with -1 cylinder 180. So you can easily see that there will be no change in the spherical power of the prescription when you change from the gross retinoscopic to net retinoscopic value, right? So this is our first problem. So the second confusion comes in case of the presbyopic power given or presbyopic addition. Presbyopic addition. So there will be three different concepts. Okay. So the three different calculation. So the three different calculation. First one is the patient distance refractive correction, the power for distance. Second one is coming for the addition, the extra power which required to see at near. And third is coming the near power. So when it comes to the near power, no, it will always comes as distance plus addition. For example, I am telling, if a patient distance correction is +2 with -1 90 degree, and suppose for example patient age is 47 years, okay, so according to age you will give the add of plus 1 point, for example I give here plus 1.50 diopter addition. Okay, so this is the distance refractive correction. This is the only addition power. But when you tell about the near power, the power of the near zone of that spectacle, so it comes will be, you just add this spherical value to this addition, so it will comes as plus 3.50 with the same cylinder 90 degree. So it will, this will be the patient near refractive power. Okay, so what is the confusion comes now? For example, I am telling, sometimes if you do the refraction and you got this power, you give this at, you explain about the progressive glasses or bifocal glasses, whatever, but patient is not interested to go with the bifocal glasses. Patient need only near vision correction. So for that case, if you give the patient a 1.50 addition, it will not become going to any kind of helpful for patient. Patient will not become clear with that, comfortable with that power. So you have to add these two, and you have to give glasses of this power, which has to be used for the reading only. And make sure, do not forget this, to give the cylindrical component, because if you miss the cylinder component, patient may complain about the letters are not that much clear. So you have to give the cylindrical component also, and you have to add this spherical plus addition power to give the full near correction. Similarly, if you go with the some myopic presbyopic case, no, suppose here if it is -2 diopter and the addition is 1.50, so then the near, what will be the near power then? Then the near power will be plus 0.50 with -190 degree. It is the near power. Okay, it is the addition power. The extra power only is called the addition. When you add this distance plus addition is equals to comes the near zone power. Right now. Okay. Now let us come with the third confusion. The importance of using the working distance in retinoscopy. When we are doing retinoscopy, you know, either we give one working distance lens in the trial frame, then we do the retinoscopy, or else after doing the retinoscopy from the gross value, we have to reduce the working distance. But the question is why? Why there is the working distance factor comes? So if anybody asks, what is the significance of working distance concept in retinoscopy? What is the significance? So the answer is, when we are talking about the definition of refractive errors, the first thing we have learned that the parallel rays of light coming from the infinity. Okay, so the parallel rays of light which comes from the infinity, and after refracting by all the ocular medium, if it is not focusing on the retina, then it is ametropia. If it is focused behind, it is called the hypermetropia. If it is focused in front, it is called myopia. If there is two different focal point, it is called the astigmatism. So all the refractive errors has been determined by the light rays which are parallel, which are coming from infinity, right? But by doing retinoscopy, if we tell by doing retinoscopy we got +1 and we tell that patient is +1 diopter hypermetropic, then we also have to send the retinoscopic light from the infinity. But it is not possible to do, right? We cannot hold the retinoscopy at infinite distance from the patient. So we have to come in a finite distance. But when the light rays comes from any near object, so this is the infinite thing, the light rays coming are parallel. But whenever the light rays comes from any near object, suppose from here the point A is a source of light, okay, and the light rays are emitting from this point A. So the light rays will be diverging in nature. They are diverging from one point, they are spreading, they are diverging in nature, right? So to make this diverging rays as parallel rays, we need to put one extra convex lens over here. We need to put one extra convex lens. This extra convex lens is nothing but is called the working distance lens. So either we need to put the retinoscope at infinity, but it is not possible. So we need to keep the retinoscopy at a finite distance from the patient. Okay. So when we keep the retinoscope at finite distance, the retinoscopic light which are emerging, which are spreading from the retinoscope is diverging in nature. So to make this diverging rays is as a parallel rays, we need to put extra convex lens, and this extra convex lens is known as the working distance lens. For example, during doing the retinoscopy, what is the distance between patient and retinoscope? Suppose if this is the patient eye, this is the patient eye, the distance between retinoscope and the patient eye is 67 centimeter, right? So for a 67 centimeter distance, the light rays has a divergence of -1.5 diopter. So to neutralize this -1.5, we need to give one +1.5 over here as working distance. If this distance is reduced to 50 centimeter, then this divergence will be -2, and similarly the working lens will be +2 diopter, right? So this is the concept of working distance and the significance of working distance used in the retinoscopy, right? Okay, thank you.